Hello and welcome to another episode of the AUBG Office Hours podcast. Today's guest is Professor Orlin Stoytchev. Welcome to the show. How are you feeling?
I'm feeling good.
Okay, we can start with the usual questions. First of all, can you tell me a little bit more about your education, where you got it?
Okay. I got my undergraduate degree from Sofia University, the physics department. I was studying mostly theoretical physics. And then I worked for 3 or 4 years in the Bulgarian Academy of Sciences before going for graduate studies at Virginia Tech. That was from 85 to 1989. I studied there mathematical physics in the mathematics department of Virginia Tech. Generally speaking, in the States, mathematical physics is considered more part of mathematics than of physics.
Okay, and from then on, when did you come to teach here at AUBG?
I came in 1997, which is 26 years ago.
And you teach in which department?
When I came, we still didn't have departments. There were 3 divisions, and I was in the science division, which included natural sciences, mathematics, and computer science. And then there was a restructuring, and ours is now the Department of Mathematics and Science, and I'm in this department.
Okay, and which courses do you teach in this department? There's quite a lot, but...
I usually teach... let me say that because I'm a mathematical physicist, I'm interested both in mathematics and in physics, and especially in the intricate connections between the 2 subjects. So that's quite long and deep topic, the connections, how mathematics influences physics and how physics influences the development of mathematics. So anyway, I usually teach 2 physics courses, which are part of the general education program, and 1 math course. The math courses that I teach vary between more elementary, like Linear Algebra, Calculus 1, and every now and then I teach Calculus 3, Calculus 4. This is sort of my prerogative. I'm the one who teaches Calculus 4 at the AUBGs, at least for now. And now with the gradual development of the physics major, there is also a need for more advanced physics courses. So, for example, this semester I'm teaching quantum physics, which is quite difficult and quite advanced and modern, I would say.
We'll get back to the connections between mathematics and physics a bit later on, but my last introductory question maybe would be for you to talk about a little bit about the skills and knowledge that we obtain from these courses.
The main skill that I'm aiming at this is the skill to think. Which is very important, and unfortunately not every one of the students is used to these things. So of course, this involves lots of different aspects. In mathematics, you learn how to structure your way of thinking, how to put together different pieces of information, different theorems that you learn in order to solve all kinds of problems. I'm constantly struggling with this. My aim, my goal is to teach the students to be able to use the things that they study to analyze and solve all possible problems. Very often the students want just to learn some recipes for solving specific problems, and I keep telling students this is not what studying should be about. You have to get the knowledge and the skills to be able to tackle any problem in your future lives, in your future professional lives. So this is more about mathematics. In physics, things are somewhat different. You have to develop understanding of the world around us, how it works, natural phenomena, because physics is a natural science, and how to apply mathematical methods and mathematical theories to model physical phenomena. So this is the main goal when I teach physics, to make the students understand how you, from observing some phenomenon, you come with a mathematical model which describes this phenomenon, how you can use this to make predictions, how important making predictions is. So this is a large part of the type of skills that we try to develop in our students. And in addition to this, since the students get to do some laboratory exercises, they have to develop also many practical technical skills. How to measure things, how to measure them precisely, how to come up with the most convenient and efficient way to measure, and so on. So different things.
You say that students often try to get the shortcut, so to just learn the formula, do it on the exam, and be done with it. But how do these skills in thinking, how are they developed in the context of mathematics and physics? Does it come through repetition, through solving multiple problems? What's the effective way to actually obtain these?
You constantly try to push them to think by inventing different problems which stimulate thinking and understanding, rather than just developing the algorithmic knowledge and skills. So this is in mathematics, this is a very serious issue when I teach mathematics. Very often the complicated algorithmic things the students learn to do pretty well, and when there is a simple problem which can be solved just in 1 minute or 2 minutes if you understand the theory, they find it difficult. This is a problem. I call it kill the student with a simple problem. Very often they learn to do the more complicated technical problems, and then one which is simple if you understand deeply the theory kills them. We don't want to kill the students.
Of course. Do you, there's, I think, I've heard this a lot, this common notion that math isn't for everyone and, specific people are better at it than others. Do you think that because it's part of the general curriculum, like both the science courses and the mathematics courses, do you think that there's such a thing as someone who is just incapable of doing math, or is that something that is invented?
I have heard a lot of this, and I would say that every person who is smart enough can do mathematics. Of course, some people are more gifted than others in mathematics, but the way we teach mathematics here in AUBG, everyone who is capable of some level of logical thinking can learn. And one of the problems with mathematics is the preconception with which students come. And this is often due to the way mathematics is taught in high school, and also physics. Because I see a lot of students, for example, who come with certain mathematical skills from high school, but they do not have the understanding. But that's not the biggest problem. The other problem is students who come with the concept that they are very bad in mathematics, and they discover that they are not so bad in mathematics, but simply the way they were taught in school was such that they found it very dull and difficult. In some sense, this is also true for physics, where in school, especially in most schools where they do not have labs, physics is taught purely theoretically, without attempts to explain how the laws were discovered, the laws of physics. Rather, here is Newton's second law, this is the equation, and now you start applying this formula for solving different problems, and then continue like that without actually paying attention to, okay, how did we learn this thing? It's not so important to tell you this is the truth. It's more important to explain how people learned that this is the true description of a phenomenon. The true is in quotation marks, because nothing is perfectly certain and perfectly true.
That's great to hear, and leads me to think, because, I took one of the physics courses with you, and we had the lab exercises, which were dedicated to this specific point, to show and to illustrate these theories. My question would be, were the empirical exercises always part of the science courses here, even back when you just started teaching, or was that something that was implemented gradually and then with the new science lab came to be?
The idea has always been to include some laboratory component in the physics courses. In fact, as far as I know, physics started to be taught at AUBG in 1995. There was an American guy from 95 to 97. He was a friend of mine who was studying in the physics department of Virginia Tech, graduate student. And so he came here and taught physics for 2 years, and he had to improvise to do some practical exercises. So, for example, the way he measured with his students the gravitational acceleration G was by dropping watermelons from the roof of the main building and measuring a bunch of students standing down on the square with stopwatches and taking the time for which the watermelon falls from the roof to the... And of course, this is not a very precise way to measure the gravitational acceleration, but I remember that when I came in 97, for a few more years, students were telling me, do you know how we measured with Professor Soli the gravitational acceleration? So it made it obviously quite interesting and exciting for them. So now, when I came, I started to try to add different types of experiments. It was a lot of improvisation, a lot of my personal effort, bringing different metal beams, rails. I had to, for example, bring some aluminum metal rails, 4-meter longs, which I had to put on the public bus from Sofia to Blagoevgrad to transport them to here, so that I can organize some kind of experiments in mechanics. And gradually I developed a set of lab exercises, but they were just in each one was just a single setup, and you can do this lab exercise with 3 or 4 students at a time. So I had to take groups, 3, 4 students at a time, then the next group. It was quite difficult for me, and the equipment was not very professionally looking. And thankfully, about 4 years ago, the administration of the university decided to dedicate a nice room and some money, so we equipped the current science lab, which is in this building, in the other part of the building. And now we have for most of the lab exercises, we have 4 parallel setups. So 12 students can work in groups of 3 in parallel. The equipment, some of it was bought, some was custom made by me or ordered to be made for our lab. So it is still developing. I'm still trying to add new and new exercises. In a couple of months, we will receive a nice piece of equipment, so-called Mach-Zehnder interferometer, which we will use for different experiments in wave optics, and also hopefully for holography. So this is just one example of one piece that is going to be added. It will be here by next year.
That is very great to hear. You mentioned, I was really struck by the watermelon dropping example. And I wanted to get back to what you said earlier about how students come here and see that they're carrying some prejudice, maybe that here they are disproven that they can do math, for example. Have you seen, specifically in the science courses, specifically in the physics courses, a point where a student kind of starts gaining a lot of interest in the subject, even though he may not be studying it for his major or anything of the like, but just through showing them that there is a different way to look at these things, that they get excited about it, for example. Has that happened?
Yes, it does happen. And of course, this is the greatest reward for a professor, to see a student who changes their attitude towards the subject. The labs in the physics courses are very useful for this, because students find them this is across the board. Students always say that they find the labs the most interesting part of the courses. And they have a lot of fun also doing these labs in most cases. For example, last night we had a lab where they were shooting metal balls with some toy guns, measuring the speed with which the ball leaves the gun, calculating kinetic energy, potential energy, trying to prove some conservation laws, conservation of energy, conservation of momentum. And it was quite chaotic, but also I think most students found it interesting. So that's just one example, but yeah, students do find the labs interesting, and they think this is important part of their education in physics. As for mathematics, this is also something that happens occasionally. A student who first takes a math course as part of the gen ed and finds it interesting. And strictly speaking, higher mathematics, university, college mathematics is much more interesting than high school mathematics in general. And they decide to do mathematics major after having come with different plans to the university.
That's great to hear. Well, maybe we can shift the conversation a little bit. Can you tell me about what got you concretely into science?
I don't know. My parents were medical doctors, and probably they hoped that my brother and I would also become doctors, but we became physicists. So actually, as a child, I liked to play with different gadgets, to take them apart, and then the funny thing is when you take apart a complicated toy and you use the parts to make something much simpler, but this is something that you have made yourself, and you're very proud about with this. And I was thinking, okay, I will be doing something like engineering or robots, things like this as a kid. I also like to do chemistry experiments. But gradually, somehow, I decided that I would study physics in the university, and this was my study in the physics department of Sofia University. I shifted from the more practical things to theoretical physics. This is what I studied as an undergraduate student. Then when I went to Virginia Tech, my initial idea was to do more like theoretical physics. Modern things at that time were string theory, quantum field theory, of course. But somehow my path was more and more towards mathematics. And my PhD my PhD thesis is more or less purely mathematical work with potential application to physics. And so in fact, my research is in mathematics, such parts of mathematics which are of potential importance to physics, like group theories, symmetries, and stuff like this. And at the same time, because I have been doing a lot of things with my own hands, so I find also interesting and challenging the other aspect, how to construct an experiment for the physics lab. What is the best way? How to refine it? I keep thinking, okay, this didn't work very well. Can I change it so that the measurement is more precise? So that's a completely opposite thing, but compared to pure mathematics, very practical things, but I enjoy this also. It's again a mental challenge.
That's a nice touch of creativity, and I want to take this back to the beginning of the conversation when you mentioned that you were interested in the connection between mathematics and physics. Can you elaborate more on that and what it means to you?
I have always been excited about this. Basically, if you think about some of the most important mathematical theories, they started being developed for the purposes of physics. In fact, calculus, which is derivatives and integrals, calculus 1 and 2, let's say, it was developed mostly to a large extent by Newton. And he developed it for the purposes of mechanics. He was developing the laws of mechanics, which are known as Newton's second law, Newton's third law, and Newton's law of universal gravitation. So he needed the relevant mathematical tools, and he, of course, he has a famous phrase: "If I have seen so far, it is because I stood on the shoulders of giants." So not everything was invented by Newton, of course, but he played the biggest role in the advancement, together with Leibniz, in the advancement of this part of mathematics, calculus. So there are many such examples, more modern things like, let's talk about classical things, still classical things, differential equations, the theory of differential equations, which again, this is mathematical tools to describe the evolution of systems. For example, how things develop in time, some quantity, how it changes as a function of time. Again, this was developed mostly for physics. Nowadays, people are using such methods in economics, in political science, and many other areas. On the other hand, when mathematics starts to be developed, then there is internal drive. Mathematicians, start to think of new connections between the different mathematical theories. They discover new theorems, and this gives feed back to physics, and very often the new developments in mathematics influence back the development of theoretical physics. Such examples for example, group theory, which is a mathematical theory, basically the mathematical theory of the symmetries of the world. It starts from the needs, from the practical needs to describe symmetries, real symmetries. So you can say that physics has influenced the initiation of these developments. But then this theory has advanced extremely much, and it has given back to physicists understanding and knowledge, for example, of such things as the properties of the electron. The electron, which has so-called spin 1/2, has very peculiar properties. If you rotate an electron by 360 degrees, its quantum state is not the same. It is multiplied by -1. So a rotated electron by 360 degrees doesn't look exactly the same, which is kind of strange. We cannot imagine how this happens, but mathematics has explained how this can work. Because these are quantum systems, so things are not very intuitive.
Well, there's some of these fun abnormalities maybe that occur in nature that don't seem intuitive to the human mind, but they are there. Can you give some other examples, for example, to illustrate this point? Can you think of any?
Other examples?
Other examples, yeah, like the rotating electron, but similar.
Well, maybe this is not a direct answer to your question, but the other thing that I was going to comment about is how mathematics can influence physics is Einstein's general relativity theory. He had some ideas that gravity is due to the curving of space-time, so it's somehow a geometrical theory of gravity, but he didn't know the necessary mathematics that is used to describe such curved spaces. But this theory had already been created, just purely theoretically, mathematically. It is called Riemannian geometry, the theory of the geometry of curved spaces. So Einstein learned the mathematical theory, used it, wrote the famous Einstein-Hilbert equations of general relativity, and then other people used these equations and found out that there is a solution of these equations which predicts the existence of black holes. So black holes, for example, were at first predicted purely mathematically as a solution of a certain set of equations that are supposed to describe how gravity works. And then these black holes have been observed indirectly already. We believe that they indeed exist. So again, this is a very peculiar object which is difficult for the human mind to grasp, because in a black hole, all the mass is concentrated at one point with 0 dimensions, which is something that cannot be understood. But this is what the theory seems to suggest.
All right. Since we're on the topic of space, and I took electromagnetism. What was the last name? Quantum physics and relativity, I think, was the name of the course.
Yeah.
So I think some of the more the physics of the mechanical, the classical physics of what is happening here on Earth, maybe is not the most interesting part for generally. Maybe we can say for most students, but space, at least to me, has always seemed like it intrigues even people who are not really interested in physics. So maybe going off what you just said, can you elaborate a little bit more about astronomy? Maybe why this study maybe is perceived better or is seems more interesting? Or do you actually agree with the statement?
What is more interesting?
Astronomy compared to maybe some of the classical mechanics for most students, let's say. Do you think that's the case? Or
astronomy is a different subject from what I teach. I teach a little bit of relativity. I touch a little bit the topic of general relativity. It's just 1 or 2 lectures. Astronomy, by the way, I have taught astronomy for several semesters. It is a very special science. It has a lot of physics, but it has also a lot of information which is purely observational information about the planets, the stars, distances, sizes of the stars, magnitude of the stars, luminosity, how much energy they emit per unit time, and so on. The interesting thing about so let's talk more generally about astronomy and cosmology, because they are closely related. The interesting thing for me in astronomy is that you have to use some very indirect methods to learn things about the celestial bodies. Some are simple, some are much more difficult. For example, a simple one is, how do we know the temperature on the surface of the sun? About 6,000 degrees. We know it from the spectrum of the light emitted by the sun. There is a physical law which tells you that if you find the peak where the wavelength which with maximal intensity in this spectrum, it is continuous spectrum, you can determine the temperature of the body that has emitted this light. So from the spectrum we know the temperature of the sun. From the spectrum of the light of a distant star we know the temperature on the surface of this star. Some are much hotter than the sun, some are colder. This is relatively simple. How do we know distances to the different objects? This is another interesting, for me, piece of science. This is the famous ladder of distances. The closest objects to the Earth, like the moon and the planets, and then the sun, more or less we use more direct methods. For the moon you use geometric methods, essentially measuring angles and distances on the Earth to determine the distance to the moon. Then to determine the distance to the sun is more complicated. Then to determine the distance to other stars which are in our galaxies but not very far, how do you do it? Well, you use the fact that the Earth is actually changing its position because it is orbiting the Sun. So you're seeing this star from different angles relative to the more distant stars. Its position changes a little bit. This is called parallax. So you measure the distance to this star. And then it becomes much more complicated when we talk about distances, for example, to objects which are other galaxies. We use there a different physical effect, which is the Doppler effect. You look at the spectrum of the light coming from the distant galaxy, you discover that the spectra are shifted with respect to the normal spectra which we observe here on Earth. And from this shift, you know that this galaxy is moving with some speed from us, getting away from us with certain speed. And then there is a fundamental law, Hubble's law, which tells us that the speed with which an object is receding is proportional to the distance of this object to the Earth. This is the expansion of the universe. So the further an object is, the faster it is moving away from us. And the only way we know the distances to very distant objects in the universe is by, essentially the only way, is by measuring this Doppler shift. So the way we have learned, we have acquired this information, this is of course over the century, starting from antiquity when people were measuring already distances to the moon. Until nowadays, this is a whole sequence of steps in which you can extend your knowledge.
And then there is also cosmology that you mentioned. Maybe briefly state what the difference is.
I'm not an expert in cosmology. It is a very fast developing science. There are, again, it is the ways we acquire knowledge about the general structure of the universe, about the very distant objects, is very complicated, very difficult. These are very difficult observations and very difficult observations. So things are changing, things are developing. We had certain beliefs 10 years ago, until 10 years ago. We know since the 1950s that the universe is expanding. This is Hubble's law, which I already mentioned. But everyone believed that the rate of expansion would slow down. The universe is expanding, but eventually it may stop expanding, or at least it will keep expanding with smaller and smaller velocity. Why? Because of gravity. Gravity tends to pull things back together. So after the Big Bang, they were shot moving away from each other, but gravity pulls them back together. And then so I remember teaching astronomy and telling them about different theories about the expansion of the universe. Will it continue expanding forever, even though it is slowing down? Will it be expanding and then it will stop expanding and start shrinking again? These are alternative scenarios. But nobody expected what was discovered about 10 years ago, that it is actually expanding with an increasing rate, which still has no generally accepted explanation. What causes this increasing rate of expansion? the effect is called dark energy. Now I read things about the new telescope, James Webb Telescope, and some data that it provides, which seems to contradict our current knowledge about the Big Bang and the way this is the so-called standard cosmology model. It seems to be questioned now by some new results by James Webb, but I'm not very familiar with these new developments.
I learned a lot from that explanation. We can take things back to Earth, I think. Maybe as we approach the end of the conversation, maybe you can talk about some of the events on campus that are organized related to science, because I know I think it was last year or last semester we had an observation, a telescope to watch a partial, what's the word? Eclipse, yeah, partial eclipse. So can you tell me a little bit more about such events on campus when you organize them?
I'm afraid that we do not have too many of these. These observations, they were part of the astronomy course. My colleague Todor Popov organized this observation of the partial eclipse. At some point, we had big plans to receive a grant, like $500,000 for the physics, for the science lab. And part of this plan was to build a dome on the roof of the Bulgarian Academic Center and put a telescope under this dome, which would be controlled from a distance, remote controlled, and would be equipped with a camera so students could make observations sitting in the lab on their monitors, but it would be live observations. Unfortunately, the foundation that we were applying for funds didn't approve this project, and so we could not do this. It would have been fun. Now, regarding these astronomical observations with the telescope that we have, it's a good telescope, but the logistics is a little bit difficult because it's quite heavy, the large one. It's 200 millimeter reflection telescope. So you have to bring it down, put it outside. There is a lot of light pollution. So you need, in order for good astronomical observations, you need a very dark place. You have to go somewhere far from the city, where the skies are perfectly dark. And then you can see much better different objects. Here we put it in the yard. There is light from all over the place, so observations are not very adequate. On the other hand, when you put it in the yard and students are passing by, it draws their attention, not only students, but the kids who play on the grass, they also get excited. So these are our potential future students of AUBG. I remember I made one observation last year like this. The colleague who was teaching astronomy, she was teaching it online. I was on campus, and she asked me to do these observations, and I set the telescope on the lawn. And unfortunately, only 2 students came to the observation, but there were kids playing soccer, and all of them got very excited. How much is it paid for this? It is free. And so they could see, I think we looked at Jupiter, Saturn, and at the moon. at that time, and it was rewarding to see these little children, grade school age. They stopped playing soccer and came to look through the telescope. But no, we do some visits when we have open house. Occasionally, I have performed some demonstrations in the physics lab for potential students. I don't know why we do not do such events for current students. But again, I haven't thought about it, but if it's not organized well, usually you won't get too many visitors for such an event.
Could be an opportunity to explore. I have one last question for you, and that is, what advice would you give to current students or to prospective students? It doesn't have to be specifically about mathematics or physics, just in general.
To find a job which they will find interesting. This, I think, is the most important thing. Of course, it is good to have a well-paying job, but I think that it is at least equally as important to do something that is interesting to you. That's, I think, the most important one.
That's a great note to end it on. Thank you for being my guest, Professor, and thank you for tuning in.
You're welcome.